Hey everybody, here we go. Forces on parallel wires. So far we've seen there's forces that are exerted on single wires. We know that there are, when they're in a magnetic field, we also know that when electricity is running on a wire, it makes a magnetic field. So you need to think about two wires. I'm going to show you videos in class as well that are parallel to each other. They're both making a magnetic field and they're both carrying current in their own magnetic fields, and it's going to cause a force. All right, so let's talk about this. So two parallel wires, they carry current, carrying current. They create their own magnetic fields and they interact. Essentially, you can think of them like being magnets. The force between them is going to be in newtons. Because they're straight wires, there's no 2 pi. It's the 2 times 10 to the negative 7th. And since there will be 2 wires, we have 2 currents, both in amps, the length of the wire in meters, and the separation, which of course needs to also be in meters. All right, so let's do one practice problem. And again, I'm going to show you, this is one I can't demonstrate. You need a lot of current to make this happen. So I'm going to show you videos. And I may even show them before this. All right, so I have 2 wires of length 2 meters. So L is 2 meters. Doesn't matter what the 2 lengths are, it's only what's in common. So if one's 2 meters and one's meter, then you can only use the 1 meter. One has 3 amps, one has 1 amp. So I1 is 3 amps, I2 is 1 amp. It doesn't really matter which one's which. And they are separated by 10 centimeters. So that's distance, and that's 0.1 meter. Got to convert. All right, so let's do the force equals, so K is 2 times 10 to the negative 7th times 3 times 1 times 2 meters, all divided by 0.1. Let's do it. Clear. 2 second EE negative 7 times 3 times 1 times 2 for the meters, divided by 0.1. 1.2 times 10 to the negative 5th. Just double checking my answer. Looks like it's good. 1.2 times 10 to the negative 5th newtons. Okay, forces are in newtons. All right, so which way do they travel? Which way do they go? So we're going to use current. It wouldn't really matter whether these were electrons or current. The way you look at it, it's the same thing. When they go in opposite directions, it's kind of works out weird because it's different than what magnets do. Opposites would attract. Well, here, when they're in opposites, they will push apart. Okay? And when they're in the same direction, again, it doesn't matter if I'm talking electrons or current flow, they will attract as if they were pulling together. So I usually put the arrows there. All right, so this is a really quick one, and you're going to do a little practice with these. Okay, bye.